Hello friends, in today's video, let us discuss free carrier concentration in semiconductors. So, we have seen in band theory about the formation of energy bands in materials, and based on the bands, the structure of the bands and the gap between them, we can classify materials into metals, semiconductors and insulators. So, particularly we need to understand two bands. The electrons, when they are filled up in a material, the last filled energy band is called the valence band, where the final valence electrons are filled in a material. That band is called valence band. And the next band, the next energy band, is the conduction band. So at 0 Kelvin in a material, the valence band will be filled completely or partially depending on its electron configuration, and the conduction band will be completely empty at 0 Kelvin. But as temperature increases, electrons from the valence band can move into the conduction band and hence make conduction happen. In a metal, the valence band and conduction band overlaps or are at very close ranges. So electrons from the valence band, when they get a little bit of energy, can absorb that energy and move into the conduction range, move into the conduction region. A semiconductor is a material where the distance between the energy gap between the valence band and the conduction band is very small. So a little bit of energy is required to make conduction happen. Insulator is a material where the width between the valence band and the conduction band is very large, and hence even when a huge amount of energy is applied, the electron is not able to reach the next band, the conduction band. So it is very difficult to bring conduction in an insulator. So this is how we could classify the materials as metals, semiconductors and insulators based on their band structure, based on the band theory. Now moving on to the concept of free carrier concentration in the semiconductors, which is our topic today. First of all, let us consider an intrinsic semiconductor. That means a pure semiconductor. So as we have said, in a semiconductor, the energy gap between the valence band and the conduction band is very small. And even at a small temperature, for example, room temperature, the thermal energy, the energy due to the temperature, which is the thermal energy, is sufficient to excite electrons from the valence band to the conduction band in a semiconductor. So even at room temperature, you can see some of the electrons from the valence band will be excited and move to the conduction band, leaving a hole behind. So if an electron leaves from the valence band to the conduction band, the electron will be in the conduction band and it will leave a hole in the valence band. So if plenty of number of electrons are leaving the valence band, gaining energy and moving into the conduction band, there will be plenty of holes in the valence band, and similarly electrons will be in the conduction band. So these electrons and holes can carry charge in a semiconductor. So in the case of electrons, we define the mobility of the electron by the term mu e, and we define the mobility of the holes by the term mu h. So if we apply an electric field into the semiconductor, both electrons and holes both can carry charge in the semiconductor. So as we see in this picture, if an electric field is applied on a semiconductor material, the electrons will be flowing against the field. Here the electric field is towards the right direction. The electrons will be moving opposite to the direction of the applied electric field, and the holes will move along the direction of the electric field. What will be the velocity of the electron? VE equal to mu E into E is the velocity of the electron, and the velocity is in the opposite direction as that of the applied electric field. And the velocity of the hole is given by mu h into E, where mu h is the mobility of the hole and the velocity is in the same direction as that of the electric field. And since the electron charge is negative, the current constituted by the holes as well as the electrons are in the same direction. That is, the positive charge is flowing to the right means current is along the right direction due to holes, and electrons are moving to the negative direction means the current due to electron is also in the positive direction. So the mobility of both the electrons as well as the holes constitute a current along the direction of the applied electric field. Now, thinking about the concentration of the charge carriers in a semiconductor, as we have said, the reason for the electrons and holes is temperature. It is thermally generated in an intrinsic semiconductor. Thermally generated electrons and holes. So as you can see, since excitation of an electron from the valence band to the conduction band creates a hole in the valence band, as we have said earlier, in an intrinsic semiconductor, the number of holes should be equal to the number of electrons. If Ni is the number of electrons in an intrinsic semiconductor, it should be equal to number of holes in the intrinsic semiconductor. Now, we have said how these electron-hole pairs are getting generated in a semiconductor. So the reason for the formation of electron-hole pairs in an intrinsic semiconductor is temperature energy, the thermal energy, and the process of this electron-hole pair generation is as we have discussed. And at the same time, there is another process called recombination. So once an electron-hole pair is formed, it is not staying as electron-hole pair forever. Sometimes a moving electron can meet up with another hole in their path, and they will meet each other and annihilate. So that process in which an electron and hole meet up and get annihilate is called recombination. So two processes are happening at the same time. One is the process of generation of electron-hole pair, and the second one is the process of recombination of electron-hole pair. And in a stable semiconductor at equilibrium, these processes, generation and recombination, are in balance. That means if I define the rate of generation as G of t and the rate of recombination as R of t, these two processes are balanced. Generation is equal to recombination. And logically, we know if the concentration of the electrons and holes are greater in a semiconductor, then the chances of them meeting up is greater and the chance of them recombining is greater. So you can surely say that this recombination rate should be proportional to the concentration of electrons as well as the concentration of holes. So R of t should be proportional to Ni into Pi, or I can say this is equal to a constant into Ni into Pi. So how did I write this equation? So because logically we know if the electron concentration and hole concentration are higher, then the recombination should also be higher. That means electrons and holes will be meeting up too frequently and recombining frequently. Similarly, that will also increase the generation rate. So I can say they are proportional to Ni into Pi, the product of concentration of electrons and holes, and I put a constant of proportionality K here. That is a factor which depends on the material K. Now since Ni and Pi are equal, I can change this as K into Ni square. Since Pi is equal to Ni, I can write it as K into Ni square. So one factor you need to remember here is I can define, since Ni and Pi are equal, Ni into Pi is equal to Ni square in a semiconductor. This Ni is called the intrinsic charge carrier concentration of the semiconductor. So this is the first equation that we will be studying in the case of an intrinsic semiconductor. We learned that the concentration of electrons and holes are equal, and we learned that Ni into Pa equal to Ni square, and the rate of recombination and generation are equal. So let us have a quick idea about the value of the intrinsic carrier concentration in a semiconductor. So for example, in the case of germanium, which is an ideal semiconductor, the energy gap is of the order of 0.75 electron volt. And if you consider the intrinsic carrier concentration of a germanium at 300 Kelvin, it is 2.4 into 10 raised to 19. So Ni is approximately 2.4 into 10 raised to 19 electrons per meter cube at 300 Kelvin at room temperature. But the density of the germanium atoms per meter cube is approximately 4.4 into 10 raised to 28 atoms are there per meter cube. So this much number of atoms are there per meter cube in a germanium, and this much number of intrinsic carriers are there per meter cube. So if you do the math, you can prove that there are about 5 number of electrons out of these atoms, only 5 atoms out of about 10 raised to 10 atoms is actually providing electron or hole. So you can see there is a huge number of atoms present in a germanium crystal, and out of this a very little concentration of atoms is actually contributing to the conduction in a semiconductor. Whereas you compare it with a metal, in the case of copper, the number of electrons per meter cube is 10 raised to 28 electrons per meter cube. So you can see there are plenty of number of electrons per atoms, and almost all atoms are providing electrons for conduction. Whereas in the case of a semiconductor, this is the case of copper. In the case of a semiconductor like germanium, if you take 10 raised to 10 atoms, out of that about 5 atoms will be contributing electrons or holes. So that is the limitation, or that is the small value. That much little value is the concentration of intrinsic charge carriers in a semiconductor. Now moving on to the case of an extrinsic semiconductor. So as you have studied in your lower classes, in an extrinsic semiconductor, we will be adding certain impurities to make conduction more. So in the case of an extrinsic semiconductor, you will either add a donor impurity or an acceptor impurity. Suppose the number of donor impurities that you add is denoted by Nd, and the number of acceptor impurities denoted by Na. Adding a donor impurity will turn your semiconductor an N-type semiconductor, because it will add more and more electrons into the system, into the semiconductor, and adding an acceptor impurity will turn the material into a P-type semiconductor. So these donors and acceptors, adding of these donors and acceptors into the semiconductor will release more electrons and holes into conduction. So even if these donors and acceptors are not present, we have seen there are thermally generated charge carriers. Thermally generated electron hole pairs are already there. And in addition to that, we will be adding these donors and acceptors. And for these donors and acceptors, the energy required for electron emission or for generating a hole by an acceptor atom is very less. So even below room temperature and even at very low temperatures, the donors and acceptors are able to release their electrons and holes. So we have seen the thermally generated electron hole pair generation depends on temperature a lot, but the electron supply or hole supply from the donor atoms and acceptor atoms takes place even at very low temperatures, because they require very less energy in order to be released. And hence, in an n-type semiconductor, as we will see later, we can find that the electron concentration is approximately same as the concentration of donor atoms, because these donor atoms will be releasing all the electrons into the system that they have. And similarly, for a p-type semiconductor, the whole concentration will be approximately same as that of the number of acceptor atoms. So we will discuss about these results after moving into a little bit more discussion. And one more thing that I need to mention is that when we add these donor atoms and acceptor atoms into the semiconductor, these are added in very little quantities, very small quantities. Their concentration is very small compared to the parent semiconductor, and these impurities do not appreciably affect the thermal generation and recombination process. So on the one hand, this will be releasing electrons and holes, but the normal thermal generation and recombination process of electron-hole pair will also be continuously happening. Electron-hole pair will be getting generated due to temperature within the crystal, within semiconductor. And overall, if the total concentration of electrons in the semiconductor, which is doped, suppose it is Np, and the concentration of holes, suppose it is Pp, where the P represents a p-type semiconductor, N and P represent electron concentration and hole concentration. So even in an extrinsic semiconductor, the product N into P remains the same, Ni square. So earlier we have seen Ni into Pi. For an intrinsic semiconductor, it remains Ni square. But even when we add more number of donors, releasing more holes into the system, more number of donors adding more electrons into the system, or even if we add more holes into the semiconductor, suppose if we add more number of electrons into the system, then the concentration of N electrons will be going up. So that means the added electrons can now combine with the existing holes, decreasing the concentration of holes, isn't it? Earlier there was a balance between the electrons and holes, but now since the electrons are more, they will be combining with more number of holes, decreasing the concentration of holes. So anyway, this concentration, this product of concentration of electrons and holes, even in an extrinsic semiconductor, obeys this equation. N into P is equal to Ni square. So when the concentration of the majority charges is increased in a intrinsic semiconductor by doping, the concentration of the minority charges will be decreasing so as to maintain the concentration Ni square a constant. So this equation, the one which we have mentioned in the case of intrinsic semiconductor, is valid in the case of an extrinsic semiconductor as well. Here you need to remember, if we are adding electrons, then the N will go up, but the concentration P will go down. So I will give you one example for this. For example, suppose in an intrinsic semiconductor there were 10 number of electrons initially and 10 number of holes initially in an intrinsic semiconductor. So as you can see, there are 20 number of charge carriers within the intrinsic semiconductor. So what is Ni into Pi? 10 into 10 is equal to 100. Ni square is 100. Suppose we are making this an n-type semiconductor by adding more electrons, and suppose I make the number of electrons to be 100. Then the number of holes will be decreased by these added electrons because they will combine with the electrons to a very low value. So what is the new Ni square again? It is 100 into 1, which is equal to 100. So Ni square is constant in the case of intrinsic as well as extrinsic semiconductor. The added electrons decrease the concentration of holes. But in this new semiconductor, how many number of charge carriers are there? 101. So you can see the number of charge carriers is increasing when we make an extrinsic semiconductor. It is only that the product of Ni into Pi remains a constant, Ni square. So this is the concept that I was mentioning. No need to worry about whether the concentration is not increasing or not. It is just the product of Ni into Pi that is remaining a constant. As you will see, the charge concentration is actually increasing. As you can see in this example, 10 plus 10 is just 20, but 100 plus 1 is 101. The number of charges is actually going up when we make an extrinsic semiconductor, but the concentration, product of the concentration will remain a constant. The change is such that this product remains Ni square itself. Now let us further discuss about the concentration of electrons and holes in the semiconductor. So since the material, a semiconductor, is neutral, even if we add electrons or holes, acceptor atoms or donor atoms, the semiconductor as a whole is neutral. So this charge neutrality demands that the total charge, positive and negative charge, should balance each other. So suppose there are P number of holes in a semiconductor, then P positive charge is there. In addition to that, if there are some donor atoms which are supplying electrons to the system, we know donor atoms are actually positively charged because releasing an electron will make them positively charged. So the total positive charge of this semiconductor is P plus Nd. Similarly, the total negative charge is the number of electrons plus total number of acceptor atoms. Acceptor atoms are negatively charged because they are actually binding an electron which is not theirs onto them. So N plus Na is the total negative charge. So if a semiconductor is to be neutral, these two terms should be equal. P plus Nd, the total positive charge, should be equal to the total negative charge. And we have the before mentioned equation, which is Ni into Pi equal to Ni square. So we will be solving these two equations in order to get a very beautiful explanation about the concentration of electrons and holes in an extrinsic semiconductor. So this equation implies that this is not Ni, this is actually Np into Pp. We are mentioning about an extrinsic semiconductor. This is either Np, Pp or Nn, Pn. So let me just write N into P equal to Ni square. The extrinsic semiconductor can be either P-type or an N-type semiconductor. So let me just write N into P equal to Ni square. So this implies electron concentration is given by Ni square divided by P. And the hole concentration is given by Ni square divided by N. So substituting these equations, let us substitute equation number 1 into this equation 3. So substituting for N in terms of equation 1, we have P equal to Na minus Nd plus N. Na minus Nd plus N. So in terms of equation 1, it is Na minus Nd plus Ni square divided by P. Now multiplying throughout by P, the equation will become P square minus P into Na minus Nd plus Ni square. Sorry, actually it is minus Ni square. Minus Ni square equal to 0. So I have multiplied with a P throughout and I have taken all the terms to the left hand side. So this is the equation. So this is a quadratic equation of the form ax square plus bx plus c equal to 0. So what is the solution of this kind of equation? It is given by x equal to minus b plus or minus root of b square minus 4ac divided by 2a. So using this equation into equation number 4, we can calculate the P concentration to be equal to minus B. What is B here? B is Na minus Nd. So minus of minus Na minus Nd is simply Na minus Nd plus or minus root of B square minus 4ac. So Na minus Nd the whole square. Na minus Nd the whole square minus 4 into 1 into what is C? C is minus Ni square into minus Ni square minus Ni square minus Ni square, so divided by 2a, which is 2 into 1, 2. Now simplifying this, we have Na minus Nd divided by 2 plus or minus root of Na minus Nd the whole square. I am going to take this 2 into the inside of the square root. So it will be written as 4 and minus 4 into 1 into minus Ni square, which is plus 4 Ni square divided by 4. So I have taken this 2 and written as a split term under the Na minus Nd the whole square divided by 4 plus 4 into 1 into Ni square divided by 4. So this is the equation for the concentration of holes in a semiconductor. This 4 will get cancelled and we have obtained the equation for hole concentration. Similarly, you can solve the same equation that we have written. This equation 3 can be solved by substituting 2 into this equation. So instead of P, you can substitute Ni square by N and you can solve this quadratic equation, and by solving so you will obtain the concentration of holes N to be equal to Nd minus Na divided by 2 plus or minus root of Nd minus Na the whole square divided by 4 plus Ni square. So this is the equation that we will get if we use this other equation. So as we have seen here, we have two equations for concentration of holes and concentration of electrons in a semiconductor. These equations are actually applicable to both intrinsic semiconductor and extrinsic semiconductor. So as we know, in the case of an intrinsic semiconductor, the concentration of acceptor atoms and the concentration of donor atoms are both 0. So in that case, as you will see, P will be equal to just Ni and N will also be equal to just Ni. The other terms will be 0. So in that case, for an intrinsic semiconductor. Ni equal to Nd equal to 0 and N equal to P equal to Ni, as we have seen already. Now let us check the cases for an N-type semiconductor and a P-type semiconductor. Those are two special cases. An N-type semiconductor, we have, so N-type semiconductor. In an N-type semiconductor, we have plenty of donor atoms. The concentration of donor atoms is very much greater than the intrinsic carrier concentration, and the concentration of the acceptor atoms is almost 0. There are no acceptor atoms, and all the atoms that we add are donor atoms, and its concentration is very much greater than the normal intrinsic charge carrier concentration. So what will be the number of holes in this case? P will be equal to, so as you can see, Na is 0. Substituting Na to be 0, we will get minus Nd plus Nd into root of 1 plus 4 into Ni square divided by Nd square whole divided by 2. Whole divided by 2. So as you have seen here, I have taken an Nd as common to the outside of the square root. So in this equation, Nd is taken as common to the outside of the equation. So that will make this term as 1 and this term as Ni square by Nd square. I have also taken the common square root, this 4 in the denominator, as simply as the denominator itself. That is why I have a 2 here. So you can simplify and prove that this concentration P is equal to minus Nd plus Nd root of 1 plus 4 Ni square by Nd square divided by 2. So the second term is actually a square root of 1 plus 4 into Ni square plus by Nd square. We know to expand such a series, what is 1 plus x whole raised to 1 by 2? 1 plus x whole raised to 1 by 2, if x is very small, can be expanded as 1 plus 1 by 2x plus minus 1 by 8x square and so on. So this can be serially expanded. Similarly, we have, since Ni is very much smaller than Nd, this factor x is very small here. So I can expand this square root term as a series expansion. So doing like that, we can get the concentration P equal to minus Nd by 2 plus Nd by 2 into 1 plus 2 times Ni square divided by Nd square. So you can just substitute the terms and cancel in your own textbook and prove this. So this is equal to minus Nd by 2 plus Nd by 2 plus 2Ni square by Nd square, which is simply Ni square divided by Nd. So this is the concentration of holes in an N-type semiconductor. So since Ni is very much lesser than Nd, we have already stated that condition. We know this concentration of holes is very small in an N-type semiconductor. Similarly, let us calculate the concentration of electrons in an N-type semiconductor. So it is given as N equal to Nd by 2 plus Nd by 2. So you can just go to your equation, standard equation. Here Na is 0 and Nd has a value. So substitute that and simply solve that equation to get. And instead of the square root term, I am going to write the series expansion, which is 1 plus x by 2. So 2Ni square by Nd square will be the remaining term. So this is equal to Nd plus Ni square by Nd. So simply you can see the concentration of holes is Ni square by Nd and the concentration of electron is Nd plus Ni square by Nd. So that is a very big quantity. We have Nd added here, which is the number of donors. So compared to the number of donors, this Ni square by Nd factor is very small, and this is approximately equal to the number of donor atoms itself. So as we see here, in an N-type semiconductor, the electron concentration is same as the number of donors and the hole concentration is very small, which is Ni square by Nd. Now as a small assignment, I give it to you to calculate the electron concentration and hole concentration in a p-type semiconductor. So what is the speciality of a p-type semiconductor? In the case of a p-type semiconductor, number of acceptor atoms is very much greater than Ni and the number of donor atoms is 0. So in such a case, use the existing equations for N and P to calculate the electron concentration and hole concentration. So you can just try and prove that the electron concentration and hole concentration is just similar to the N-type semiconductor case. So I hope this portion is clear for you. In today's session, we were discussing the concept of electron concentration and hole concentration. First, we mentioned the case of an intrinsic semiconductor. We have learned an equation Ni into Pi equal to Ni square. Then we learned about the value of this concentration. Then we discussed the case of an extrinsic semiconductor, the source of its charges. Then we discussed an equation about the electron and hole concentration. Then we wrote the equation for charge neutrality, which is P plus Nd equal to N plus Na. And using these two equations, we solved for an equation for electron concentration and hole concentration. Then we use this equation to find the electron concentration and hole concentration in an N-type and P-type semiconductor. In an N-type semiconductor, and as an assignment, you have to find the electron concentration and hole concentration in a P-type semiconductor. I hope this portion is clear for you. Thank you.